This is part 2 of our gas laws discussion. So in this video, we're going to talk about two more gas laws, the ideal gas law and Dalton's law of partial pressure. We're also going to calculate the density of a gas and molar mass of a gas and look at mole fractions to determine the pressure of a gas. Let's first start with the ideal gas law. The ideal gas law now brings in a fourth variable, and that fourth variable is the number of moles of gas. Now, before, we haven't really talked about it. I mean, we did talk about it in terms of increasing pressure or decreasing pressure. Remember, if we put in more gas particles, it'll increase the pressure. But other than that, we haven't really talked about it. We haven't used it in calculations or anything like that. So the ideal gas law talks about the number of moles, and it also gives you set conditions. So it gives you one pressure, one volume, and one temperature. This is the formula for ideal gas law. PV equals nRT. It's also known as Pivnert. So P again is pressure, V is volume, N is the moles of gas, R is a universal gas constant, and T is temperature. And remember that temperature is always in Kelvin, right? So never degrees Celsius. So R is a universal gas constant, and there are actually two values for this R. There's 0.0821, and then there's 8.314. Now, if you take a look at the units, what is different about these is actually the pressure unit. Okay, so we have liters, atmospheres per mole Kelvin. Here we have liters, kilopascals per mole Kelvin. So if your pressure unit, because that's what it depends on, if your pressure unit is atmospheres, then we're going to use the R value of 0.0821. If your pressure unit is in kilopascals, then we're going to use the universal gas constant of 8.314. Now, these two values are always given to you. It is not something that you would memorize. So let's take a look at problem number 1. Determine the temperature in Kelvin of 2.49 moles of gas contained in a 1-liter vessel at a pressure of 143 kilopascals. So the first thing you should notice here is that you are given moles, and so that indicates that you'll be using the ideal gas law. Other things to look for is that you're given set values, so just one value for volume and one value for pressure. So we're going to use this formula, PV equals nRT, and we're going to go ahead and define the variables first. So moles, you would put for N, 2.49 moles, you have volume, 1.0 liters, pressure, you have 143 kilopascals, and you're looking at the pressure unit to determine your R value. Remember, R is a universal gas constant. So pressure is kilopascals, and take a look at your notes. Which universal gas constant would we use with kilopascals? We would use 8.314, right? Because that's where the pressure units match, okay? So kPa and kPa, and we're solving for temperature. Let's go ahead and plug it in into the formula. We're solving for temperature. So we're going to multiply, divide. You'll see that the like units will cancel out, kilopascals, liters, and moles, and you're left with Kelvin, which is great for temperature, and we get a value of 6.9 Kelvin. So remember, with this, you're not adding 273, you're not subtracting 273. You have a final unit of Kelvin, and that's exactly what you want. Problem number 2, calculate the volume that a 0.323 gram sample of hydrogen gas will occupy at -8 degrees Celsius and a pressure of 0.90 atmospheres. So the first thing you'll recognize is that moles are not given, but instead we have grams. So by now, you know that grams can be converted into moles, and this is grams of hydrogen gas, so that we could easily convert that to moles of hydrogen gas. So we know that we're using the ideal gas law. So let's go ahead and define our variables. First thing is we have grams. You can convert it now. I'm just going to go ahead and write it in for N, and I know that I'll convert it later before I move on. And then we're given temperature, -8 degrees Celsius, and a pressure of 0.90 atmospheres. So now for the R value, again, you're focusing on your pressure unit, and which R value will you be using this time? You'll be using 0.0821 liters atmospheres per mole Kelvin, right? And we're solving for volume. Now, before we move on, we actually need to do two things. one, we need to convert our grams to moles, and two, we need to convert our temperature, degrees Celsius, to Kelvin, right? It's always Kelvin for temperature, never degrees Celsius. So let's go ahead and convert our value to moles first. So we see that it's hydrogen gas. Remember that hydrogen is diatomic. So it's not just H, but it's actually H2, right? So you're going to need your periodic table right now, and we're going to use the fence to convert our grams to moles. So we have 0.323 grams of hydrogen. We're going to copy the unit down, grams, and we have moles on top. So take a look at your periodic table. What is the mass of H2? 1 mole is equal to 2.02 grams, right? So we're going to go ahead and divide those numbers to get a value of 0.160 moles. So we're going to go ahead and erase 0.323 grams, and we're going to replace it with the number of moles we just found. And again, we got to take care of temperature, right? So remember what we have to add with 273 Kelvin. And you get a value of 265 Kelvin. So now that we did all the conversions, let's go ahead and plug it in. We're going to solve for volume, and volume is 3.9 liters. Now, we can use the ideal gas law and make several derivations from it, so that we could solve for mass, we could solve for molar mass and identity of a gas, and that we could also solve for density. So, for example, if I want to solve for molar mass, I'm going to use PV equals nRT, and we're going to replace N with this mass divided by molar mass. So if you think about what we're doing in the fence, when we set it up like the fence and we convert grams to grams to moles, this right here is exactly what we're doing. We're just doing mass divided by the molar mass, right? So if we replace N with these two things here, then we get a new formula, PV equals mass times R times T divided by molar mass. That's essentially what it is, okay? Because some of the problems might give you the mass of a gas, like our previous problem, and there we easily converted it and solved for it. But again, you can also use this formula here as well. Now, we can change it around to solve for molar mass. Okay, so we can just bring molar mass out from the denominator, right? And you do, you multiply, you divide, and you can rewrite it so that its molar mass is equal to mass times R times T divided by P times V. Okay, so let's bring density into this. So density is mass over volume. And if you see here, we can replace this part with simply density. Okay, so if we do that, we have density times R times T divided by pressure. Okay, and again, you can rearrange this formula so that we can solve for density, and you'll see that in our next couple of problems. So in our next problem, it says, what is the molar mass of a gas if 7 grams occupy 6.20 liters at 29 degrees Celsius and 101.3 kilopascals? What is the identity of the gas? So we're going to use one of the formulas that we derived. So this wants molar mass, so we're going to go ahead and use this formula. Molar mass is equal to mass times R times T divided by P times V. So let's go ahead and define our variables. We have 7 grams for the mass. We have volume of 6.20 liters. We have 29 degrees Celsius for temperature and 101.3 kilopascals for pressure. The R value, we're looking at the kilopascals. So for that, our universal gas constant is 8.314, and molar mass is what we're trying to find. So once we have all this, let's look through it, see if we need to do any conversions prior to setting it up. If you look at temperature, it's in Celsius, so we want to go ahead and change that to Kelvin. So let's add 273, and we get 302 Kelvin. So we're going to plug that all in. and like units will cancel out. And you see here that grams and moles don't cancel out, so you know that your final unit is going to be grams per mole, and that's exactly what you want, right? Because molar mass, we know, is grams per 1 mole, right? So we're going to multiply and divide, and you get a molar mass of 28.0 grams per mole. So now that we have the molar mass, what is the identity of this gas? So you're going to take a look at your periodic table, right, and you're going to look for the molar mass that is closest to this value. So go ahead and take time to do that. And what do you think it is? If you said silicon, you are incorrect. Even though silicon's molar mass is 28 point something, silicon is not a gas, right? Silicon is a shiny solid at room temperature. So that metalloid is not a gas. If you thought, okay, then phosphorus, because that's a nonmetal, phosphorus also is not a gas at room temperature. And so you have to think about then your diatomic elements, right? So for this, it's actually nitrogen, N2. Okay, so 1 nitrogen is 14.01 grams per mole, N2 is 28 grams per mole, right? So that's the identity of the gas for this problem. Problem number 4, calculate the density of carbon dioxide at 546 Kelvin and 4.00 atmospheres. Well, we're going to use one of the formulas that we derived from the ideal gas law. Molar mass equals density times R times T over P. We can change this around to solve for density. So density equals molar mass times P over R times T. So let's go ahead and define our variables. So here, the first numerical value that you are given is temperature, 546 Kelvin. You have pressure, which is 4.00 atmospheres. You see that the pressure unit is atmospheres. So what is the R value that you are going to use for this problem? 0.0821. And what else can we figure out from the information that's given? We can figure out the molar mass of carbon dioxide, right? So do you remember the formula for carbon dioxide? It's CO2. So you're going to go ahead and take a look at your periodic table, add up the masses, and you should get a molar mass of 44.01 grams per mole. So let's go ahead and plug in all those numbers. I'm going to solve for density. Remember, density's unit is grams per liter or grams per milliliter. Here we have grams per liter. And density of this gas is 3.93 grams per liter. The last gas law that we're going to talk about is Dalton's law of partial pressures. So Dalton's law of partial pressure states that each gas in a mixture mixture exerts pressure independently of the other gases present. So if we look at this picture, let's say we have 3 different gases, hydrogen, oxygen, and nitrogen. Each of the gases will exert their own pressures. So gas 1 is 200 kilopascals, gas 2 is 500, and gas 3 is 400 kilopascals. And so if we were to put these 3 gases in these containers into one container, so all together, the total pressure that is inside this container of the mixture of gases is equal to the sum of the individual pressures. Okay, so in this case, you just add it all up and you get 1100 kilopascals. So to put it into a formula, we have the total pressure is equal to the pressure of gas 1 plus pressure of gas 2 plus pressure of gas 3, and it could be more than that, right, depending on how many gases that you might be given. So let's take a look at our first problem. What is the partial pressure of hydrogen gas in a mixture of hydrogen and helium if the total pressure is 600 millimeters of mercury and the partial pressure of helium is 439 millimeters of mercury? So you can probably already figure this out, but just to give you a visual of what's going on, inside the container we have 2 gases. We have hydrogen gas and helium gas. It has a total pressure of 600 millimeters of mercury, and the partial pressure of helium is 439 millimeters of mercury. What is the pressure of hydrogen? So, can you figure it out? All you have to do is set it up like this, right? The total pressure is equal to the pressure of hydrogen plus the pressure of helium. We are given the total pressure. You're given the pressure of helium, so you just subtract the two numbers to get the pressure of hydrogen, which is 161 millimeters of mercury. Problem 6, you are given percentages. So if the air from a blast furnace contains a total pressure of 3.7 atmospheres and 85% of the air is oxygen and 15% is nitrogen, what is the partial pressure of oxygen near a blast furnace? So again, just to give you a visual, you have two gases, oxygen and nitrogen. You notice that these percentages equal to 100%, right? So you have a total pressure of 3.7, nitrogen is 15%, oxygen is 85%. In other words, you can think of this as, because you're trying to figure it out for oxygen, it's basically what is 85% of the total? What is 85% of 3.7 atmospheres? Okay. If you want a formula, you can use this. We're actually going to use it for our next problem. So the pressure of oxygen, in this case, gas A, is equal to the total pressure times the percent, or it could even be a fraction of that particular gas. So when we set it up, we have 3.7 times 85%. Now remember, you can't just multiply by the percent, so you have to convert the percent to a decimal. So we have 3.7 times 0.85, right? We just divided by 100 for that percent. And you get a total of 3.1 atmospheres for the pressure of oxygen. Let's take a look at our last problem. Problem 7 states that if the total pressure is 6.36 atmospheres, what is the partial pressure of nitrogen if I put 2 moles of nitrogen and 3 moles of hydrogen into the container? So here, again, we have two gases. We have nitrogen gas and we have hydrogen gas. You're given the total, but you're not given the pressures, the partial pressures, the individual pressures of nitrogen and hydrogen, right? What are you given? You're given the number of moles. So if we set it up, we can set it up like this. 6.36 atmospheres is equal to 2 moles of nitrogen plus 3 moles of hydrogen. But with this, you can't really solve anything, right? But is there a way where we can actually convert two of these numbers into a fraction or even a percent? We can, right? So total from here, these two gases, we have a total of 5 moles, okay? So if we were to put that into a fraction form, 2/5 of it is nitrogen and 3/5 of it is hydrogen. Now, if you hate fractions, and I know we never deal with fractions in chemistry, so if you want to convert that to percentages, that's fine. You're just doing one extra step to solve this problem. So this is really similar to the problem that we just looked at, problem number 6, okay? So we want to know the pressure of nitrogen. So we have the total pressure, 6.36, and we're going to multiply that by 2/5. That's it. And you get the total pressure of nitrogen, and that is 2.54 atmospheres. And those are all the gas laws that you need to know for this class.